All right, so today we're diving into a really big challenge in medical nanotechnology. How do you build the perfect little vehicle to deliver drugs? I mean, something that can carry its precious cargo safely and let us track it inside the body. Sounds great, right? But what happens when the delivery vehicle itself is actually the problem?
Yeah, what happens when that delivery vehicle is chemically reactive? When the very thing you've designed to carry the cure, well, it ends up destroying it before it even gets where it's going. That's the huge paradox we're going to unpack today.
So right at the heart of all this is a really fascinating material, the porous silicon nanoparticle. On one hand, it holds incredible promise for medicine, but on the other, it has a pretty dangerous, destructive secret. So here it is. This is a raw porous silicon or PSI particle. The easiest way to think about it is like a microscopic backpack. See all those little holes? That porous structure gives it a massive internal volume, which is just perfect for packing in a ton of drugs. And what's even cooler, it naturally emits light. That means we can actually track it in real time inside the body.
Now, this combination of therapy, that's the drug, and diagnosis, the tracking, is the whole idea behind a field called theranostics. It's kind of the holy grail of this kind of medicine, delivering a drug and then watching it work, all with the same particle. Sounds amazing, right? Well, with raw porous silicon, there's a big catch.
And here it is. This is the fatal flaw. Raw PSI is super unstable. Once it's in the body, it degrades really quickly. That handy tracking light we talked about, it just fizzles out. And worst of all, its surface is chemically reactive. This is something called redox activity. And what it means is that the particle itself triggers chemical reactions that attack and destroy the very drugs it's supposed to be delivering. It's literally a carrier that poisons its own cargo. The first attempt to fix this was basically a brute force method. You just bake the particles at really high temperatures. But this so-called cure? Yeah, it turned out to be almost as bad as the problem itself.
And the trade-off here is just awful. I mean, look at this. The goal was to stabilize the particle, right? And sure, thermal oxidation does do that. But the cost? Well, it completely kills the light emission, so it's not trackable anymore. Plus, it swells up the pore walls, which slashes its drug-carrying capacity by 10 times. That's just an unacceptable compromise. You lose everything that made it special in the first place.
So clearly, scientists needed a much more elegant solution. Instead of just burning the particle, what if you could wrap it in some kind of protective cloak? And that's where polymers come in. The researchers in this study decided to pit two main contenders against each other to see which one could create the perfect coating.
Okay, so here are our two contenders. On the left, we've got a biopolymer called chitosan. You might know it. It's derived from things like shrimp and crab shells. And on the right, a really well-known biocompatible polymer, polyethylene glycol, or PEG for short. The goal was simple. Figure out which one of these could create that perfect protective cloak for our nanoparticle.
So, to find the winner, the coated particles were put through a gauntlet of 4 really critical tests. First, surface charge. Second, drug compatibility. Third, loading and release. And finally, fourth, optical stability. This is how we're going to pick our champion.
All right, let's get into the results. We're about to see which one of these coatings actually solves the problems of porous silicon without creating a whole bunch of new ones.
Okay, round 1, surface charge. Now this graph shows a huge difference right away. At a pH of 7.4, which is basically the pH inside our bodies, the PEG coating has a strong negative charge. We're talking a Z potential of about minus 38 millivolts. But the chitosan coating? It's the complete opposite. It's highly positive at over plus 48 millivolts. And as you're about to see, this fundamental difference in charge, well, it changes everything.
Now you might be thinking, okay, surface charge, so what? But does this actually affect the drug that's tucked away inside? The answer is a huge yes.
So let's look at round 2, drug survival. The results here are just staggering. When they loaded these particles with a model drug called cobinamide, the SPI PEG particle showed 0 reaction. The drug was perfectly safe. But the PSI chitosan particle? It triggered a reaction that completely destroyed the drug in less than an hour. Gone. So the takeaway here is crystal clear. The PEG coating creates this stable, non-reactive shield. It successfully neutralizes that destructive redox activity from the silicon core. It's that negative charge that creates this perfect shield protecting the drug. And that's something the positively charged cytosine just completely failed to do. Not even close.
All right, on to round 3,
drug loading capacity. And I mean, just look at this chart. The difference is unbelievable. The chitosan particle could only hold about 18 milligrams of the drug for every milligram of silicon. The PEG particle, 225 milligrams. That is more than 12 times the carrying capacity. This isn't even a close contest anymore.
And now for the final round, round 4, optical stability. This is the ultimate test. Can the particle keep its tracking light on over time? Well, as you can see from those top lines on the graph, the PEG-coated particle's light emission stayed incredibly stable for 90 days. In a biological solution, preserving its quantum yield like this is an absolute game changer. It means you can actually track these things for long-term applications.
And hey, don't just take my word for it. The researchers themselves pointed out how big a deal this was. They actually said, and I quote, "To the best of our knowledge, this stability has not been reported till now." Basically, this was a first. They had really truly created the perfect cloak.
So what's the bottom line here? What are the big takeaways for anyone out there looking to design the next generation of these kinds of platforms?
Well, it really boils down to 3 key things. First, you absolutely need a polymer coating to neutralize that destructive redox activity of porous silicon. No question. Second, polyethylene glycol, PEG, is without a doubt the superior coating. It protects the drug, it gives you a huge loading capacity, and it keeps the optical tracking working for months. And third, chitosan, despite sounding good on paper, just isn't suitable. Its positive charge and reactivity make it a non-starter, causing drug decomposition and really poor loading.
I mean, what this research gives us is a powerful, stable, high-capacity platform for theranostics. The engineering problem has, in a very real way, been solved. So the real question now is, with a vehicle this good, where do we go from here? What diseases are we going to target next?